All right, now on this one's kind of tricky. Which one of these graphs do you think is AC volts? It says which graph shows an AC voltage. Oh, this ain't the tricky. That's an easy one. Would be the top left here, right?
Yeah. Yes.
That one wasn't either. I think it's the next one. It says no, it ain't this one either. It says now click to the point of the tab, the lab scope. I'm sorry. It says click the point in the lab scope image where the voltage is at its most negative. So remember, this is the zero line here. Anything above is positive. Anything below it is negative. So the most negative should be around here. Somewhere around here, correct?
Yeah. Yes, correct.
Alright. Let's go to the next one. That was right. Click on the point on the last scope image where the voltage is 0. Well, that's easy, right? Go across this 0 line. This is 0. Go across here. And that's correct. A. Click the point in the last scope image where the voltage is at its most positive. So above this is the positive side. So the most positive should be around here. Okay? So now we go to the next lesson. Now it says, let's think about you putting in a crank sensor, permanent magnet crank sensor, and the gap is too wide, the magnet gets weak, or gets smaller. If the coil itself is weak, the amplitude also of the signal gets weak. This is what this is telling you. Right there. So here, the number of turns. This is a increased number of turns. You see how big it got? Now, let's say half the coil was weak or got shorted. Watch the signal. See how smaller it gets? A situation I can recognize this too is when a car will run off idle because the magnetic field gets the permanent magnet signal or the AC signal gets bigger, and I can trigger a module or the computer. But at lower speeds, because the coil winding is so weak, it can't trigger a module because the amplitude, the height of it, is so small it cannot trigger the module. And this is showing you that. Look at the magnetic strength. I'm going to increase it. Look how wide it gets. I'm going to a low strength or weak magnet. Look how small it gets. When the speed increases, the signal gets bigger. So a situation like this is, I have seen cars that when you increase the RPM, the car will run. But at a lower RPM, the signal got so weak, the car wouldn't run. And here's somebody, the gap, it gets closer. Look at the signal. The gap, somebody set the gap, like a crank sensor or a cam sensor, too wide. Now look at the signal. I went the wrong way. I went the opposite direction. That's closer. This is further apart. Now it says here, yes.
Mr. Davis, I have a question.
Go ahead.
Sorry to ask you this. On this type of sensor, analog sensor that creates AC signal, can we call frequency every time the sine wave goes to 0 and to the maximum peak or the minimum peak?
I'm sorry, say what you was breaking up. Say it one more time.
Oh, on this type of sensor, on this type of graph, the one we're looking at,
Yeah.
can we measure by frequency the amount of sine waves they pass through every time they cross 0 to the 0 point?
Yeah, you could do it with a lab scope and a set of cursors, you can. But one of the main things on this one, I'll be more concerned about the amplitude, the height.
Amplitude.
Yeah, because if that amplitude is weak, if that magnet is weak, the amplitude is going to be small. That can cause a problem.
Okay, but my question is if we can call it also frequency, or frequency is just applied to digital signals.
No. Frequency, right? What you're seeing right now, frequency is the amount of time to turn on off per second. This is the right now. This say I can say 1, 2, 3, 4. This is about 5 times per. Let me see. This is about 10 times per second right now.
Yes.
Right. That's the frequency. If I count this correctly, I'm looking at 5.5 a second. So it's about 10 times per second. That's your frequency. It's like 5 times and a half a second. So a second that'd be 10. So this right here is like 10 times per second. That's your frequency. As you increase the speed, what's speed at? If I increase the speed, you see it? My frequency increases. Yeah, frequency is something. How many times something turn on and off per second? Answer these questions here. It says, how can you generate an AC voltage? You can generate an AC voltage by using a stronger magnet. You can generate an AC voltage by moving a magnet near a coil of wire. Or you can generate an AC voltage by increasing the rotation speed. Which one is true? 1, 2, or 3? Pick one, y'all. Any, mini, money, mo. Somebody pick one. Come on,
Will B?
B? Let's check it. There you go. It can generate AC voltage by moving a magnet near a coil wire. That's correct. Change the rotation speed of the magnet a number of times. We already did that already. As the rotation speed increases, you gotta pick one of these. Does the voltage produced increases? The voltage produced decreases. The voltage produced remains the same. Which one is true?
A.
A. Yeah. Change the strength of the magnet a number of times. We did that over here. See, this is what they're talking about. We already did this already. What happens to the amount of voltage generated when a magnet becomes stronger? The voltage produced stays the same when the strength of the magnet field increases. The voltage produced increases when the strength of the magnetic field increases. The voltage produced decreases when the strength of the magnetic field increases. Which one? A, B, or C?
B.
B?
I would say B.
Very good, Joe. Very good. Change the number of turns in a coil several times. It said change the number of turns in the coil. Because I go that way, I increase it, amplitude, I get smaller, less number of turns, it gets small, amplitude gets smaller. I increase it, it gets bigger. What happens to the amount of voltage generated when the coil has fewer turns? The
B.
amount of B?
C. Oh yes, B. I'm sorry.
The amount of voltage generated increases. Nope. Look at the question. What happens to the amount of voltage generated
C.
when a voltage has fewer turns, less
Oh,
turns?
the fewer
Yes.
decreases.
Which one is it?
C.
C. There you go. Change the distance. Strength, rotation, distance. Here I'm decreasing the distance. I'm closer. This sort of like you're adjusting a pickup coil or a crank sensor. This is close. This is further away. You can see when it's further away, it's smaller. When it's closer, it gets bigger. Oh, you can watch this. I didn't even notice that. You can watch the magnet. Watch. I'm going to go further away. See it moving further away? I'm gonna get closer. Oh, I just noticed that. What happens to the amount of voltage generated when the distance between the magnet and the coil increases? The generated voltage decreases as the distance increases. The generated voltage remains the same as the distance increases. The generated voltage increases as the distance increases. Which one you think is this?
A.
Which one? A?
A, number 1.
This trying to charge me.
A. Exactly right.
Meaningful charge.
Oh, this one's a little. This one may be a little trickier. Alright, so in which graphs can a full AC cycle be seen?
Bottom left. Oh no, it looks like the top right.
Top right, yeah. This one can fool you because it is. Look at this. This is one cycle. This is. I'm sorry. This is one. So this is. I'm sorry. One.
Negative and then positive.
Two. I'm sorry. Yeah, it's half. One. This is starting another one. All right. So this is the correct one. But this will fool you though, because you think it's a whole cycle because it's doing it again. Right, but it's not. It's actually more than one. This is half, full, one, half. It's like 1.5 right here. So this is actually one cycle. 1/2, the second half. The animation shows a turning magnet. Press the stop button when the voltage is at 0. So basically, if I get to 0 here, I gotta stop the buttons. So I gotta play catching games here. Ah, that's not it. Man. This is stupid. I should be able to slide it.
Yeah.
Ah,
Really?
Come on. Come on, stupid. Oh, so close.
Yeah.
I wonder if I check it that close when they let it go by. Oh, they would. They did. All right, that's correct. It's not exactly 0, but I guess it's close enough.
It's close.
The animation shows a turning magnet. Press the stop button when it's the most positive. This should be easier. See, that's the most. See this? This is the most positive of that signal. Okay. You know now. Know what this is good for when it's triggering a transistor, right? Some transistors they have to see the positive side of the signal to turn it on. Oops, check. Next one. The animation shows a turning magnet. Press the stop button when the voltage is at its most negative. Alright, the last one. This is the one Arm was telling me about, this last one. Anytime it has numbers, that's when it starts to get crazy. It says, in the picture you see 2 lamps. The left lamp is connected to a DC voltage of 12 volts, which is, you can see right here. This is blue, this is red. See that blue line? That's 12 volts. Now look at this. Before it was 2 volts per division. Now it's 5 volts per division. So each division, which is a square block, is 5, 10, 15. And you can see that's right somewhere in the middle. That's how you got to 12. Okay? And this goes up to 20 up here. So it's from here to here is 5, then 10, then 15, and right in the middle that should be somewhere around 12. That's 20. So from 0 to top is 20 volts. That blue line, what this last scope is showing you here on the left, is at 12 volts. In the picture, you see two lamps. The left lamp is connected to DC voltage of 12 volts, and the right lamp is connected to AC voltage. Now this is the the red line. You can see here that says 0. I'm going here negative, and here positive, back down to 0. That's one cycle. So if I'm looking at the positive voltage above this line here, which is this 0. This is 0 when this green line is at. You can see I got about 12 volts AC. If you count it, look, I got 5, 10. Let me do this. 5, 10, 15. Right, you can see that blue line, and this red line intersect right where that blue line is at. So it's about 12, positive 12 volts. It says here, in the picture you see two lamps. Oh, I just did that. Read the voltage used to power the two lamps. Now over here, I gotta say yes or no on these three. The peak value of the AC voltage is 12 volts. Yes or no?
Yes.
Yes.
The waveform on channel A, that's this one right here, A, the blue line, is 12 volts. Yes or no?
Yes.
Yes.
Yes. The effective value. Now, effective is, where is it at? I should have kept the other line. The last scope will display peak voltage or AC voltage sine wave, but the multimeter will give you effective value. That's a multimeter of the AC voltage. The effective value of the AC waveform is 12 volts. Yes or no?
No.
Oh.
That's really good. That's real good.
Yeah, but once you start getting down into the module,
Yeah.
you actually have to do like crazy math into it.
Yeah.
Like it. I mean, like
I'm
not bitching or complaining, but like this was really difficult. This is
Yeah,
not some.
you're absolutely right, dude. Who's that? Who's that? Armin?
Yeah.
Yeah, you're absolutely right. It is tough, and make it so worse. They should give you an example of how they figure this out.
Nothing.
I had even emailed them one time. I said, "Hey, what's the example? What's the mathematical formula?" And they never emailed me. They never called me back. Never emailed me back. So you gotta sit there and for hours to figure it out.
Mr. Davis, I think for answer 3, the answer would be 8.4 volts because it is 12 volts, and then you times it by 0.707. That gives you 8.84
Yeah,
volts. Yeah, so you're below the 12 volts there.
yeah, exactly. That's how you do that. You gotta multiply 12 by 0.700 and you get 8. You're exactly right.
You could also see the picture right there where it says L2. The bulb is not as, I don't know if it's maybe my screen, but it doesn't look as yellow as the one as DC.
Hey, you're right. That's the next question coming up. You're right. You're correct.
Mm.
That's your next question here.
Oh, man.
Lamp 2 glows less brightly because, right, this is number 2 now. The lamp connected to the DC voltage glows with a peak value more than 12 volts. So it's saying this one has more than 12 volts. That's why it's glowing so bright. Is that true or false?
False.
The peak value of an AC voltage does not have the same effect. The peak value of the AC voltage does not have the same effect as a DC voltage of 12 volts. True or false?
True.
True.
The lamp connected to the AC voltage glows with an effective value of 12 volts. True or false?
False.
I check it.
I think we pass.
You good. That's good. Now, number 3 says, set the value of the AC voltage so L1 and L2 glow equally. So I got to move the slides. Now watch it. Watch this picture up here. See how it got bigger? I bet if I actually had the actual number of that and do the number now, multiply by 0.7, what the, let me see. Where's my calculator at? Just out of curiosity.
So you're
5, 10, 15, like 16 I would say. 16 or 17 I say. Let's call 17 times
That's like 16.
0.707. Yeah, I got 12. Yeah, that's 12 volts right there. I put 17 times 0.70, gave him the 12. So 12 and 12, that's why it's equal.
So that would be the formula to figure out
Yeah, this is the formula.
DC and the AC.
Yeah,
AC,
exactly. This is the formula right here. To find the effective value, calculate it by multiplying the peak value, which is 17. How I got 17? This is what I did. If y'all didn't see that, I'm going to the top of this line right here, the peak, and this is 0 here. That's 5, 10, 15, right? Now, since I don't have no cursors, I'm guessing since it's a little bit over 15, I'm guessing 16, 17. I went with 17, and it gave me 12 volts when I did the math. Hey, can y'all mute your mics unless y'all want, until the point y'all want to answer a question? I'm getting a lot of feedback. Thank you. If you measure the voltage across L2, which is this one, with a multimeter, you will measure 12 volts, the peak value, the effective value, are 17 volts. I think we just did this, didn't we? Which one do you think you get? I'm sorry. First one, 12 volts, yes or no?
that thing that looks like no.
No?
No.
How about the peak value, yes or no?
I think no, because it says the peak value is 0.707.
No, that's a measurement right here. That's how you measure it. That's a calculation.
I'll say yes. Yes.
Yeah. Yes? You don't go yes or no? You say yes or no?
I'll say yeah.
Yeah.
Everybody say yes? Okay. The effective value, yes or no?
No.
And it should read 17 volts, yes or no?
Yes.
Yes.
0.04. Oh wow! I thought hold up. I thought you got 2 on right.
That sounds like me.
What? Okay, let's do this again.
Mr. Davis, this should be the effective value.
So hold on, let's go number 1. So let's read this again. 0.4. I'm actually shocked on that one. If you measure the voltage across L2, all right. Oh, let me see something. Let me see something really quick here.
It's 12 volts.
Let me see something. All right, I'm gonna leave it right there, and I'm going number 4.
It automatically switches for you.
It goes all the way to the right.
Oh, it goes to the right on its own. Okay.
Yeah.
So if you measure the voltage across L2 with a multimeter, you will measure 12 volts.
Yes.
Yes.
How about the peak value?
No.
I would say no, and then the next one would be yes.
Should be
The
effective
effective value,
Yes,
yes.
And the last one will be no. Yeah.
value.
That's
We're good this time.
Oh, you're good this
There we
time.
go.
You're right.
We switch everyone.
That's kind of confusing, though. I'm confused on this question.
Oh, Jesus.
Question. The
That's
whole
okay.
module is confusing.
Mm-hmm.
Yeah, it says if you measure the. Oh, so we actually did this on the last slide too. We did 17 times the number. We got 12. So yeah, that one I understand why that one was wrong. Now it says the peak value. When you measure the voltage across L2 for multimeter, do you do the peak value? No, we read actually reading the whole. We reading the whole peak. We reading the whole peak to peak with a voltmeter. So this right here is peak to peak. A voltmeter reads peak to peak. That's why this is correct.
The effective value is
Oh,
the value that it was affected by the other loads on the system, isn't it?
The effective value is actually peak to peak.
No, I mean
No.
the effective value.
But this one right here,
I think the effective value would be the blue line, and then the peak value would be the highest point on the wave.
no, we're only talking about
L2.
L2.
Yeah, we're talking about L2. That means that's why it said the effective value.
I'm pretty sure effective value is peak to peak. Now this one right here surprised me. It says, let me see that. If you measure the voltage across L2 with a multimeter, you will measure. You will measure 17 volts.
That's
Oh, no.
17 volts.
I see. I got it. No, you won't measure 17 volts because you're going to go peak to peak. So a multimeter is going to give you peak to peak. So no, it won't be 17 volts. Right? No, it won't be 17. It'll be from the whole amplitude. Okay, that's what I got. Okay, I got it now. It'll be the whole amplitude. All right, I got it now. All right, so now the voltage L2 we're going to measure. So now look at the here's your meter. This is right now. This is DC. That's AC. I'm gonna switch it over to 20. So I like 20. I'm gonna put this over here. Oops, that didn't go.
No, you gotta go above it.
Above it.
You go
Right
the
there
blue.
where the lines
The
are.
blue.
Oh, right here.
Oh,
Okay, I'm
the
sorry. All
blue.
right, thank you.
At the load.
Thank you.
We need to measure at the load. Across the load.
12 volts.
There it is.
I give you the formula right here. It's the same formula. Number 6. A multimeter is used to measure the effective value. Yes or no?
Yes.
No. Yes.
Let's go with yes. An AC voltage with a effective value of 12 volts has the same effect as a DC voltage of 12 volts. True or false?
False.
False.
An AC voltage with a peak value of 12 volts has the same effect as a DC voltage of 12 volts. True or false?
False.
This is false?
I think it's true.
Let's check and see. Oh, let's change to true now. Oh man, no.
The middle one was true. It
Middle
says
was
it up
true?
there. Look at the first line.
Yeah. Yeah, the middle was true. It's a multimeter is used to measure the effective value. That's true. An AC voltage with a effective value of 12 volts has the same voltage as DC voltage of 12 volts. Yeah. Voltage with a peak value of 12 volts has the same effective value. An AC voltage with a peak value of 12 volts has the same effect as a DC voltage of 12 volts. No, see, here's the thing that gets you confused. Right, and it's showing you the slides before, because these two almost sound the same. But the thing that gives away is this is peak to peak. Remember, the bigger the amplitude, the more voltage. That's what this is, peak to peak. This is just from 0 to peak, right? So it's not as effective as this one. That's the two we drew. I put a line up here earlier. Effective value of multimeter is peak to peak. And this one just from 0 to 12. So it ain't the same number. As we look on a couple of slides back, as we move the slider, the bigger the amplitude, the brighter the bulb got. Okay, that's peak to peak. That's the effective value. This one just from 0 to 12, or 0 to peak. Now, use the multimeter here. Use a multimeter to measure the AC voltage generated by the generator. What is the voltage generated by the generator? So I go here, and I go here. I put this on AC, turn this to 20 volts. I got 14.14. Next one. Are we using the same? Calculate the peak. Calculate the value generated by the. Calculate the peak value generated by the generator. So now we have to use our formula here. I'm using the calculator here. 14.14. I wish I could bring up the other calculator. I can't, can I?
Now we need to multiply this value, the voltage value, times the 0.707.
Yeah, let me see. I can't do both of them. Oh, there we go. So we did 14.14 times 0.707 equals now 0.9, right? I can tell you right now, because an Armin called me last night, I tried this, and that is wrong. But you're doing it just like the math value says. You're doing it just like it says. It says multiply by 0.707. And every time I did it, I got it wrong. Watch. If I do this, I wrote it down here. If I do 14.114 divided by 0.707, I got 20. And I got right. And I get it right. Now, I was stuck on this thing for at least 40 minutes. I cannot figure out how do you divide when it doesn't say divide. Anybody see it? Maybe I'm seeing something wrong. Because the math formula says the effective value is calculated by multiplying the peak value by 0.70. This is also called the root mean square. Unless I don't know what the root mean square is, but it says multiply. So I multiply it, and I got 9.96, and it's wrong. But when you divide it, right, because percentage, you get 20.
You do the opposite. That's why you're looking the opposite.
Say it again.
You do the opposite.
Yeah, you do the opposite.
You're not looking for the effective value. You're looking for the peak value now. That's right.
The peak value, yeah.
The opposite of the multiplication is the division.
Exactly, and that's how I got it. I did the opposite, right? I said, let me just do the opposite of what it says, and I got the right number. And I just guessed at it, but nothing up here says to do it like that. And that's the problem with this software. It don't give you examples, like in the beginning.
This is easy, actually. As you go into the module more, it gets even more difficult.
Yeah, let me see something. The next one, number 9. It says here, The picture opposite shows an alternating current generator, which reduces the AC voltage, which with a peak of 29.20, a peak value of 21.21 volts. Calculate the effective value. Now let me see something. This says effective value.
On this one, you have to multiply it because it's asking for effective value.
Yeah. This
Yeah,
says
that's what I
peak
was
value. Yeah. You know what? Let me see something really quick. I'm just out of curiosity. I'm just trying to figure out something here, y'all. Cause I don't want to know. Times 0.707. So now this is top. That's the peak value. That's 0 to peak. All right. Now I'm gonna multiply by 2 since it's AC and see what happens. If you round this off, it's about 20.
Very close.
Yeah. Maybe that's what it is. When you round this off, that's 20.
Well, try that on the answer.
I'm gonna try it. Yep, that's what it is. Peak is from 0 to the peak voltage, and since we're talking about the AC, positive and negative, when we peak to peak, it gives you 19.99. That's what it is. See when we work together, we figure this stuff out. Now this one is 21. It just says peak value, right? So now, huh? I'm sorry. The picture opposite shows the current generator, which produces AC voltage with a peak value of 21.21. Calculate the effective value now. Now they want the effective value. So now we just multiply 21.21 times 0.707. Yeah. Number 10. It says here, the measured value is the effective volt. The measured value is the effective voltage. True or false?
False, because it's on top. It says the value of an AC voltage is 70.7 of the peak value.
All right. Next one. The measured value is 21.21 volts, direct current voltage. True or false?
That's false too.
False.
The measured value of 21.21 is AC voltage. True or false?
That's true.
True.
The measured value is the maximum peak value voltage. True or false? True? Y'all did really good on that one.
Still easy.
You know
Keep
what?
going.
You know what? I thought you got this one wrong. Which one? I thought you got this one wrong. Which one was it?
The second one?
Yeah,
with
the top one. I keep forgetting effective is different. But that was right. Y'all doing really good on this. This gonna be a little. This one gonna be a little tough. What's this? It says an AC generator produces an alternating current with a peak value of 18 volts. The resistance of the lamp is 4 ohms. What is the effective current?
You gotta use Ohm's law for that, don't you?
Right.
6 amp.
So, if I get my calculator back up here,
Then convert it and multiply it.
18 volts divided by 4 ohms equals 4.5, right? 4.5 amps, right? Yeah, agree or disagree with that?
Agree.
That's true, but then you have to multiply it by 70.7, which will give you 3.18.
For this one?
Yes, if I'm not mistaken. I spent a couple hours on that.
All right, let's multiply it by. Oh, let's see this. We're gonna get it wrong. Let's see. Right, you just put this, it would be wrong. All right, like you just said. So now, if you do this, times it by 0.707, because it wants the effective value. 0.707 equals 3.18, and that is the correct answer. This word right here, this effective value and peak value, is the whole key to everything. So we just took that first number, that 4.5, and multiplied by this. That gives us our effective value. Effective value here.
Yes, we had to the end of the year to figure it out.
Okay, here's a oh, it's another one. An AC generator produces an alternating current with an effective value again of 4 amps. The resistance is 3.5 ohms. Calculate the peak value of the voltage. How do we get voltage? Amperage times resistance, right? So it's 4 times 3.5 is 14, right? What we do next? Effective value. What we do next?
And you have to divide it by 0.0707.
Exactly. Not multiply it, you divide it, which is which they don't say up there. But we found that out. You divide it by 0.707. 1980. Arm, it sounds like you got it before we did it. It sounds like you figured it all out already.
Dude, I'm telling you, I spent 10 hours on the modules yesterday, from morning till night, and then the computer almost got launched into the yard.
Anytime you get that bad, y'all just text me and let me know and move away from it. Then we go over it in class, like we're doing now. Don't bust a brain cell doing this. Just tell me which module it was, cause I can't find. I took a minute to find them. I just need to find the module. That's the last one. That's it. Now, obviously, on a state test or my test, obviously we ain't doing no math. The whole premise, the only part y'all need to understand is this, right? How does the improper gap affect the circuit? A weak magnet affects the circuit. A coil that's partially shorted affects the circuit, right? Just this. Basically, it's just lesson number 2, right? When it comes to AC voltage and a sensor like a crank sensor, a cam sensor, or a pickup coil, right? How is that adjusted wrong or partially shorted will affect the circuit?